Okay, so let's look at the last module for this week 6 material. So we will continue our discussion where we left with the previous module, which we were looking about green and sustainable materials. So we'll look some more concept in more details today, and the concept that we will be more focusing on in this particular material, in this particular module, is how to track the material flow in an engineered system. So when we say engineered system, we are all engineers, and most of us are engineers, or we understand engineering system. Essentially, when you make something, when you make any product, the material has a flow. When we say material flow, essentially we are talking about material from its raw material, which is your mining, the raw material that you get after the mining activities, going to the smelting plant. From there it will go to a primary manufacturing plant, then it will go to secondary manufacturing plant, ultimately the product will be made. So how the material is, how to track it, and so we'll look at some of the examples over last few decades. And as you know, many of these data is mostly collected in Western European countries or American countries. So most of the time the examples we have to look at is from there. Unfortunately, in Indian context, we don't have much data right now in terms of to look at some of this stuff. So it would be really nice to look at some of the Indian examples, but unfortunately we don't have it. So we'll look at some of the examples from the US system, which is the example which was readily available. So any material has a life cycle. So you already kind of did a life cycle analysis, so you know what we mean by life cycle. Life cycle means from cradle to grave. So they are extracted from lithosphere or biosphere, then it will be processed into commodity material, then products, then it will be used and possibly reused. When we say reuse, means recycling. So we'll look at how much of certain materials are being recycled and why it is not recycled. We'll talk about those kind of stuff. It also depends on the technology. So eventually it will be either disposed or leak into the environment. So the number of times a material is reused or recycled before it really gets into the environment, that determines what kind of impact it will have in terms of a significant impact on its environmental footprint. Different use of the same material can lead to a variety of different impacts. So for example, if you're using mercury in certain products, but mercury is in a form which is essentially in a solid form, even when it comes to the disposal stream, if it stays in solid form or it is bound up with some other material, it doesn't leach off that easily, so the impact will be much less. But if mercury is in a form which when released into the environment, it gets reduced for some reason, becomes methyl mercury, and then methyl mercury can travel quite a bit because it's a volatile form. So that's then its impact will be different. So same mercury may have a different kind of impact under different environmental system and under different use. So we will try to characterize in this module. We'll try to characterize the flow and emission of material in the manufacturing sector. Also, we'll look at data on material and mineral flow, which is entering the economy, and what kind of waste, emissions, and recycling structure different materials have. So we'll take like one or two examples and try to understand that, and similar things will exist for other stuff. So when we talk about in terms of the material flow, we always look at a conceptual model. So what you're looking at here in this particular slide, this particular diagram, which is figure 4.5. Again, all these diagrams came from that textbook that I suggested, sustainable engineering textbook, at the very beginning of the class, which is also there at part of the course description. So you can access this book. It's not very expensive. Like on Amazon, on Flipkart, it's around 350 to 400 rupees. It's a good book to have, especially if you are interested in this particular topic. Or so most of the pictures came from there. So just wanted to let you know. That's why the figure 4.5 means the chapter 4, figure 5 from that particular book. So if you look at here, so we talked about the system boundary. That's what you see in the middle. That's the system boundary that we are looking at. What's the system boundary? We are looking at any particular system. That could be a kind of for a particular material. But there will be input and output. So for any particular system, we are looking at a say lead from extraction to production of lead products, and finally there will be disposal. So throughout the system, there are some inputs coming in. At the very beginning you will have the input of domestic extraction, direct or indirect. There could be some imported extraction as well. We are getting the raw material. We do that, as you will see that most of the countries do import things and exports things as well. So then these are the stuff which is coming into the system boundary. Then we have some output. Outputs is waste and emission output. Some waste is going out, some emissions are going out, and then there could be some exports as well, which is exported out of that particular system boundary. So if you think about the system boundary as the geographical region of India, for example. Now if you look at, let's see, for our argument's sake, let's see that we are talking about lead, or we are talking about iron. We use lots of iron. So we have some domestic extraction of iron which is happening in the country. We have some direct and extraction which is, then we also import iron, different quality of iron. We do import iron into the country, as you will see in one of the figure later on. And then as part of the iron process, there are several plants. Even we have Tata Steel very nearby in Jamshedpur. I am talking to you from IIT Kharagpur campus right now. So there is waste and emissions coming out. So they do have waste being product, LD slag, which is it's again a very common waste from a like a steel manufacturing plant, and then that's actually one of the big waste stream that they are always worried about. Then part of the iron in the product form, or they are also exported. So when we look at any material flow, so if we want to see how much iron is there in the Indian context, we can look at all the inputs coming in, we can look at all the outputs going out, and then we can see whatever is the left is the accumulation into the system. So we'll see some examples. So let's look at the example of lead. We know the lead is a neurotoxin. I think I talked to you about that. That there are some hypotheses, I would say, that Roman Empire, they collapsed because of the lead. They were using this leaded vessel, and this leaded vessel, they were using a lot of alcohol in that. Alcohol is lower pH, so lead leached out in those alcohol. Lead is a neurotoxin, it affects the brain, and then that's led to they becoming crazy, and then about fighting each other, and then finally the empire collapsed. Lead exposure is associated with development delays. We know that. That's why we have unleaded gasoline. I think I mentioned to you earlier in one of the earlier module that we have unleaded gasoline because lead was a problem, especially for smaller kids. It does affect the brain development, so we don't want too much lead in anything. So but lead has been used as octane enhancer in gasoline, as we know. That's why you have unleaded now. Earlier it used to be leaded gasoline. Used in batteries, many of the car batteries they still have lead. That's the lead acid battery. Lead was used in paint, lead based paint. So there are, if you look at the material flow, and for last few decades, one of the major usage of lead is in electronic industry. Many of the electronics solder that you do, soldering, when you put those chips on those, you have your printed wire board, and you put your different chips on top of that, and by the solder which you attach these chips on the printed wire board, it contains a lot of lead. So at least it used to contain a lot of lead until recently. Now we are trying to get rid of that and try to go for other materials. So if you look at lead usage in United States, we'll see in the next slide. It's the left hand portion here. It's if you can see, there are on the top part is 1970, and the bottom part is 1993-94. So here on the left hand side says the sources, in the middle we have the products, and at the end we have the fate of the lead. So, and same thing at the bottom, sources, products, and fate. So as you can see that graph has actually gone bigger in 1994 to 1970, more usage, of course, more lead is being used in 94 as opposed to 1970. That of course because of like we have more industrial processes going on, economy has gone up. So with all those things happening, of course more lead is being used. So but if you look at the recycling of lead, it was 3%. So recycling rate was 3%, but recycling rate in terms of since the total production has gone up, our recycling rate has actually gone down to less than 1%. So actually we were doing better in recycling, in 1970 as opposed to 93, 94 in terms of the percentage wise. Total wise, we are still doing a lot of recycling, more recycling in 1993, 94 because the consumption has gone up. So on the left hand side, you see the input coming in. Input is from the mines, from the battery imports or metal imports. So that's your kind of the import coming in. If you look at the 93, 94 side, part of it, then we have the product. We make different kinds of products like ammunition, solder. That's you see solder, which I was talking about. Then you make batteries, like internal consumption. Those things are over there. Then we have freight, where some of these are being exported, some are being recycled, some goes to the landfill. Then we have some is actually in the product. We don't know how much it will based on its shelf life, it will come back. So that's called future recycling. At the end of the product life, current recycling. So this is how the things are moving, and we can look at the material cycle for each and every element in more detail based on what data we have. Similarly, the things over here is a little bit not that complex because we don't have the solders and other things in here. We did have ammunition, some oxide, some gasoline. You see the gasoline in 1970, we don't see gasoline usage of lead in 93, 94 because we banned use of gasoline. So we can draw these kind of diagrams to kind of understand what is happening with one particular material. How much it's the input coming into the system boundary. System boundary usually we can take as a geographical boundary of a city, geographical boundary of a state or a country, and we can look at the net input, net output, and whatever is not will be the accumulation. The difference between the two will be the accumulation in the system. So kind of some important points from the previous slide. 1970, the fraction of recycled material was around 36%. So 450 tons out of 1250 tons of the total usage was coming from recycled material. While in mid 1990s, the fraction has increased to 65%. So we had more 910 tons of recycle plus 1400 tons of the usage. Lead is being used in variety of products, so lead-based paint, lead additives in gasoline. So that leads to more usage of lead in different products, means potentially more release into the environment. The other products like lead acid batteries can be effectively removed and recycled at the end of the product life. These days, lead acid batteries, it's almost 100% recycle in many developed countries. Even in developing countries, when you go for a newer battery, you basically give your old battery, and then that can potentially be recycled. The figure also showed that the fraction of dissipated users decreased significantly because of the phase out of many lead-based paint or lead additive gasoline. Use of lead in batteries have increased significantly as demand for starting light ignition batteries in vehicles have increased. So that kind of gives you an idea of how things have been moving in terms of for certain metal. So now if you look at a different metal, which is let's look at the global flow of iron, and we'll try to see this in different kind of scenario. We'll look at iron in 1970 and then 2000. It's a global flow. We'll look at the global flow of iron, and then we'll look at the flow of iron from the US context. So globally in the year 2000, again the numbers will go up now because more and more India, China, Brazil, these companies are booming economies since 2000. So more and more demand for iron is there, so to build a lot of steel structures. So in 2000, in 10 to the power of 9 of kg, if you look at that particular unit, we are the different things that you see over here, you see lots of arrows in this picture, and at the bottom you can see the legend which tells you which arrow means what. So thinner the arrow means lower the data. So the thinnest one is the flux is less than 10 to the power of 10 like a teragram or tetragram per iron per annum. Then when you little bit thicker, 50, then 100, 200, 500, 800, and based on that you see the error, the bars over there. So there are repository of iron. We talked about that in the previous module, that there are different types of reserves. From that reserve, you will get some iron coming out. That would be crude oil, crude ore, some iron tailings. Then the production of the iron, production will be there. Since in the production phase, again some may go back into the repository in terms of the waste and other stuff. Then you do the casting, goes to the fabrication and manufacturing, then do use, discard, waste management and recycling. Then from waste management, part of it can go to the landfill dispersion, part of it could be recycled, purchased as scrap and go back to the production. Then could be some industrial scrap which can kind of go back over here. So there could be some home scrap which can again go back to the recycling system. So this kind of gives you an idea of how the iron is under different kinds of different systems in terms of its global usage, global flow. Same thing we'll look at for the US in a minute. So there are different types of flow types we looked at different based on the different arrows that you saw. Global use of iron as a case study, what iron flows during production of products into production, fabrication, manufacturing, use and waste management. These are flows between these stages of material. For example, home scrap within the production process, you are reprocessing it. Flow of ore from lithosphere can be compared with various types of recycling, losses to environment. So those are different things we can look at. So if you think about the previous slide that we had where we look at this figure 4.7, the global material flow for iron, they typically comes from multiple sources. So if we can do a material mass balance. Mass balance is a very important concept which probably you are aware of. If you are not, I would encourage you to kind of go to any environmental book and look for mass balance, and you will find something to read about that. So it's essentially conservation of mass. That's what we are trying to look at. So material balance, we can be assessed to assess the consistency of information. We can, whatever information we have, we can do a conservation of mass and come up with those information. At the macroscopic level, basic material balance equation can be translated into crude oil flow into accumulation, determine whether the flow is a satisfied material balance or not. So essentially what we are telling is, after you get all the data regarding the mass balance, regarding the material flow, you draw that conceptual diagram. After drawing the conceptual diagram, do the mass balance on it to cross check whether the data that you received makes sense or doesn't make sense. If it doesn't make sense, that means you need to go back and revisit the data and try to correct it. Now same picture, but just for the US industry, and here you can see, since it's for the US, on the top we have another bar over there that's essentially for export or import. So things that is coming from outside. That's why we are showing it on outside of the system boundary. The dotted line is your system boundary, and things outside of the system boundary is what it says on top, other regions. So that's your things coming from out of the system boundary. So here again, some crude getting into the production, fabrication, use, disposal. So those things are there. Some scraps going in, some industrial scrap, landfill disposal, slag and byproduct. And from top, from the other regions, like from other not in US, from outside US, we are getting some iron ore coming. We are also getting some iron and steel products. We can getting some final products, and then we are also sending up some final scrap. Some scrap from US is also going abroad for managing that scrap or recycling it or whatever. So that kind of gives you some idea about the material flow for one particular. The previous one you look at the global material flow. This one kind of relates to for one particular country. So we can have similar material flow done for different metals for a particular country. So same thing. Now if you look at the China example, China we know is a booming economy. Again you see all those China is also importing some iron and steel products. It also exporting things. It also sending some scraps overseas. So that's, and then of course it's taking things from the repository and also putting some things on the repository in terms of the slag, byproducts, landfill disposal and all that. So this graph is more interesting. If you look at those two were kind of just those three, I would say, just looking at the iron flow for different countries. First starting with the global, then China, then India, then the US, then China. This one, this figure kind of tells you that what is the import and export of this iron is going on for different countries. Several countries have been listed here. If you look at India, which is right here, which is 2 bars before China. So we are looking at, Canada. So it's 2 bar before Canada is what we are looking at for Indian scenario. and you see over down here IN, that's the India. So 2 bars before Canada. So but here in the middle we have a 0 line, at the bottom we have export. So if some country shows up too much on the bottom, that means they are exporting a lot, they are not importing that much. You see some more on this side, doesn't see much here, that means they are importing a lot and not exporting. You see many countries kind of in the middle, so they are importing as well as exporting. You might be wondering why they do that, because we are looking at iron. That doesn't mean we are looking at just the raw iron seeds. We are looking at different products made of iron. So for a particular country, you might be exporting certain products made of iron, which has iron as one of the component, and you might at the same time be importing certain products which is made out of iron. So, and here on the top left, you see that iron ore, iron, so different colors, different sets of basically gray or black. It tells you what kind of products or material we are looking at. And then the line with the dot, you see that's the total net import and export. So that kind of you see over here as well. On top side is import, on the bottom side is on export. So some of these, which is the highest exporting country? Brazil. So we start from Brazil, then Australia, Russia, Canada. As we go over here, we kind of goes towards the middle of partly it is below, partly it is above. So that then it becomes kind of it is exporting as well as importing, but predominantly exporting until I would say all the way to Romania, and then it kind of gets in kind of in the balance. Then you see things being exported a lot, but here some are kind of in the balance, and but later on you see kind of an increase in more and more import. For example, US is actually the highest importer of steel. US is importing lots of products. If you go to any big shopping area in US, you see the products mostly made outside US. So that's so those products are coming in, and many of them contains a heavy amount of iron and other material. So what we saw in those pictures, it's the understanding the sourcing of materials and the geopolitical issues with some source region. We know about some of these critical material. We'll talk about that. So world leading exporter of iron is Brazil, which we saw in the picture, and the leading importer for both total exports and net imports is US, which we saw as well. Countries like Belgium, Netherlands, United Kingdom are both importers as well as auto exporter. So they import the iron as a raw material, export iron in the manufactured goods. Global trade in commodity material leads to some countries becoming net importers while others becoming net exporters. We saw that. For example, while China is a net importer of iron, it is also a dominant producer and exporter of rare earth metals. So combination of material scarcity, potential energy saving, geopolitical factors, they lead to increase in this rate of recycling and reuse of many material. So one example here, percentage of this study was done several years back, actually almost 20 years back, where they look at the percentage of metals in hazardous waste in the United States that cannot be recovered. So these are the different metals present. This is the percent theoretically recoverable rate, and so that percentage recycled in 1986. So although it can be recovered, it can be recycled, especially say for example if you look at the nickel, almost 100% can be theoretically recoverable, but only 0.% to 0.1% was being recycled. So many of them, silver for example, or vanadium, or even zinc, very low recycling, cadmium, chromium, copper, it's better, little bit better, it can be, but it could go much better. Lead was nearly 56% recycle, or mercury was 41% recycle. So, but these are mostly related to the hazardous waste, but there are other types of materials out there. This, as I said, this was a very focused analysis. This was one paper done, but it has a certain objective of that paper. So, but it just found that many opportunity existed for recovery of materials from waste, which even exists today. That there are a lot of if we can come up with a good technology for recovery of heavy metals, as most of us carry at least one electronics with us, and that electronics, as I have said, like a phone like this sometimes have 35 to 40 elements in there. So if we can extract these elements, so basically where we lack is the technology. If we can come up with a better technology which we can help extract some of these heavy metals, that will increase the recycling rate. So we have to make it economically profitable to recycle, And so analysis focused only this particular analysis that we just a table that I showed you, that focused only on hazardous waste, so not on other stream. But recycle stream was simplistic. It ignored the issues of economy of scale, so those things should be looked into. Nevertheless, the analysis does indicate the resources are not effectively recovered from many waste streams, which is even today is true. Some of that information was very old, but one recent report, and I have given you the link over here, so you can try to go and look at that particular report. So UNEP has come up with a recent global data on metals recycling, and that was done in 2011. So I would say around 5 years back. So not too bad. So analysis does conclude that global recycling rates can continue to be improved. Metals like lead, along with iron, copper, chromium, nickel, zinc, and all those have post-consumer recycling rate that exceed 50% globally. But many other metals, especially the rare earth metals, have post-consumer recycling rate of less than 1%, and it's a rare earth metal. So it's a rare. So we should try to recover it. Recovery of them. So if somebody wants to develop some technology, that's the area where we should look at how to recover these rare earth metals from electronics or other waste products. So one of the primary barrier is lack of critical information. How much lack of, say any industry would like to know how much is out there, how much rare earth. Say for example, if I tell you that you start a business of trying to recover these rare earth metals from the waste stream of India, number one question will come, okay, what's the waste stream we are looking at? How much rare earth metals potentially we can recover? Because you will start looking at your business model, and you will start looking at the economics of scale, that whether you have enough material to process and whether you will make enough money to self-sustain and make profit, because as a business you have to make profit so that you can diversify. So data on the waste quantity as well as quality is very important, but unfortunately we don't have much. And then data on the composition of waste, what is the composition, where they are located, if there is a co-contaminants. So these data are rarely available. That kind of that creates problem in terms of potential use of raw material. Many materials are still being recycled a lot. Aluminum is one good example. Aluminum cans are mostly recycled, and aluminum, anything with aluminum gets recycled a lot. And the reason for aluminum getting recycled, as you can see, and here energy input required for 1,000 pounds of primary aluminum ingot production from bauxite, and energy input required for 1,000 pounds of recycled aluminum from automotive shop. You see that it kind of goes down to almost I would say it's 24 times. So it's 24 times less, 23 times less energy is needed from recycle than from like a raw material. So that really saves a lot of energy, and it saves energy, and then of course energy, that saving of energy leads to more money being more profit margin, better environmental performance. So all these things kind of helps with that. So to summarize, material flow tracking can identify overall availability of the material, and we also potential opportunities. One way of looking at this is to change the design of industrial systems so that they are more closely resemble highly networked, mass conserving natural system, like we have natural ecosystem works and industrial ecology. The data necessary to perform detailed material tracking are just beginning to happen. India, as I said earlier also, we have an Indian resource panel now, which they will be trying to generate these kind of data either by themselves, or they will try to have people do it for them. And so for many analysis, we need to assemble necessary data for use and flow as on a case specific basis. As material scarcity becomes an important issue, which is these part analysis will become increasingly valuable. So to summarize this week, this is the last module for week 6. So for for almost every engineering design, it involves use of materials, and the materials have environmental footprint. So in this week's lecture, we were trying to methods for characterizing the footprint. We started with doing what are the good steps of doing an LCA, kind of give you an overview. When we started looking at the metals for environmental fate and transport. So involved footprints associated with extraction, processing, and environmental release of materials. But these assessments can lead to very different characterizations of material. And then also, is the material scarce? Can it be recycled? Do environmental release have significant impact? Those are things we can try to answer in this particular week's lecture material. Then, is the material scarce? Can it be? Okay, we talked about that. There are no universally accepted method for combining these characterization, or whether a material is sustainable. Multiple methods are used, so those things can be done. Engineers will need to consider material in context of particular design. Recognizing the choice of most sustainable material will be application is specific. So most sustainable material will be depends on what application you are trying to use it for. So that kind of brings it to the end of week 6 material. So as I have been telling you for last few modules that the course is, as you know, the course is already up and running. This is the 6th week. I assume that you are doing the weekly quiz. I strongly encourage you to finish all the weekly quizzes as you make progress. That will help you understand the concept, that kind of force you to do some reading. And then of course those of you who want to take the final exam will take that, and then questions will be kind of similar, starting similar to format will be similar to kind of midsem, but there will be some math problems and other things as well, which we'll talk about. So okay, so with this let's close this particular module, and then again I will see you in next module, the first one for week 7. Thank you.